Hello everyone, welcome to this second video of the series where we are going to cover rack systems in detail. If you have not seen the first video of this series and you are an absolute beginner who's trying to build and deploy a rack system, I highly recommend for you to go back and watch that video. I will add that link in the description, and probably there will also be a link at the end of this video, most probably. But if you are someone who is relatively familiar with rack systems and probably looking for some advanced level learning, you will get plenty in this video also. So the things that we are going to cover in this video are RAG evaluation. We'll go a bit deeper into how to evaluate a rack system. Second thing is RAG architecture. We'll try and understand some patterns that are probably important when you're trying to architect a rack system. Then we'll delve deeper into the world of retrievers. A rack system is essentially a retriever system augmented by a large language model. We'll try and understand and look into different types of retrievers, their advantages and disadvantages. We look at full text retriever, semantic retriever, when to use each of them. And then we'll also look at a hybrid retriever, which is a blend of different types of retriever as text and semantic. We'll close this video by building a project where we are going to build a retriever. Okay, we'll build a text retriever, we'll build a semantic retriever and a hybrid retriever so that we understand and the basics that are needed to build the subsystem of retrievers, which can be further added to a large language model and augment the generation as we move forward into this video series. So yeah, stay tuned, plenty in there, and let's get started with understanding RAG evaluation. Alrighty, before we delve deeper into the evaluation of RAG system, a quick revision of the subsystem that we discussed in our last video. Now, any rack system will particularly have a user input. Okay, I'm calling it UI here. It's coming from different user experience, different UI interfaces. It could be a chatbot, it could be an underlying system through which we're feeding data, from which essentially it could be a query. Okay, a query, it could be any kind of use case that the person is trying to solve, which is sent to the retriever, and the retriever will try and fetch the documents or the corresponding knowledge that is person needed for answering the original question from the user. Now, this is one part of the system. Okay. Second part of the system is where we send this retrieved text or retrieved information, okay, to the large language model along with the original query. And then the large language model has a task where, based on the original query and the retrieve context, it needs to generate a response which should help it solve the corresponding problem that a user is trying to solve. Alrighty, absolutely simple. The way any rack system per se works. You might see lots of different variation of these, but in essence, at a high level, this is how a rack system is supposed to be working. Alrighty, now it looks very simple. Okay, there is just two subsystems. There's a retrieval and then there is generation. We get the corresponding chunks of information that we need, added to the large language model, give it the corresponding context, and it answers, right? But there are lots of places things can go wrong. That is where the evaluations come in. Okay, if you think of it, which are the places the evaluations might be able to help us? Again, going back to the same system diagram that we were looking for. If you think of it, we are actually working with multiple stages of information. So I normally try to think of it as a subsystem level information flow, and where we can kind of we are not able to capture the corresponding data points that are needed to answer the questions properly. One of those references that I normally suggest everyone to go through is the Raga's paper. Okay, it's a great paper that came out of Cardiff some time ago, and it essentially it tells us is any rack system per se should be evaluated based on three important factors. One is faithfulness, where what essentially it means is that any answer that we are getting should be inferred from the context that is being fetched by the corresponding retriever system. What it means is, like, for example, in the use case that we are going to see right now, that is the same use case that we basically saw in our last video of our archive data set, which has like lots of academic papers. If I'm trying to ask a question about, let's say, neural nets which are used in a large language model setting. I'm just saying a random example, and I'm asking you to a particular question. The answer should be there in the context of the retrieved data that is being got to the large language model. All right, it should not, the large language model should not answer the question. We are actually working with multiple stages of information. So I normally try to think of it as a subsystem level information flow, and where we can kind of we are not able to capture the corresponding data points that are needed to answer the questions properly. One of those references that I normally suggest everyone to go through is the Raga's paper. Okay, it's a great paper that came out of Cardiff some time ago, and it essentially it tells us is any rack system firstly should be evaluated based on three important factors. One is faithfulness, where what it essentially it means is that any answer that we are getting should be inferred from the context that is being fetched by the corresponding retriever system. What it means is, like, for example, in the use case that we are going to see right now, that is the same use case that we basically saw in our last video of our archive data set, which has like lots of academic papers. If I'm trying to ask a question about, let's say, neural nets, which are used in a large language model setting, I'm just saying a random example, and I'm asking you to a particular question, the answer should be there in the context of the retrieved data that is being got to the large language model. All right, it should not, the large language model should not answer the question based on its own internal knowledge. Alrighty, that is what faithfulness essentially means, and that is what how I interpret it. Second is answer relevance. Second thing is that the answer that large language model is generating should be relevant to the question that is being asked. Okay, maybe the context that we have is quite good, it's getting added to the question, but the answer that we are getting is just not relevant to the problem that our user is trying to solve. And third is context relevance. Alrighty, the context relevance essentially means is it tries to solve the subsystem of retriever. Essentially, the context relevance is that the context that a retriever adds to the original query should be relevant to the question that is being asked. Alrighty, I said lots of things. Now, again, going back to the same thing, think of it in three particular aspects of it. Okay, like first, think of number 3, context relevance. The context that is being extracted from the knowledge base should be relevant to the question that is being asked. Second, answer relevance. That a context plus question should be able to satisfy the user's need. And third is faithfulness. Faithfulness essentially means is we should be able to answer the question only based on the retrieved context from our knowledge base. That is, at no stage we should expect an answer which is either getting completely hallucinated by a large language model, or is coming from a totally internal pre-training knowledge that has been learned over a period of time. So hopefully that makes sense. And I will just to make it a bit more concrete, let's look at a quick example, right? Same example that we saw in our last video of archive data set. I have already done the pre-processing where we have done a TF IDF of the whole data set, and it's being stored as a vector. So I won't go into the detail anyway. The code will be available for everyone. But what only change that I have made is I've added a print retrieve paper so that we are able to see the context that gets added to a particular question, and accordingly we can make a judgment or try to understand how it's doing in all the 3 parameters, right? Again, 3 parameters: faithfulness, answer relevance, and context relevance. Alrighty, again, so we have done that. What I will do is I will rerun this. Okay, so we have it here, and let's ask it a question. The question that we might probably want to ask is, can you explain chain of thought in LLMs. Okay. What happened here? Alrighty. We asked question. Can you explain chain of thought in LLMs? Let's see. Okay. So we've got chain of thought prompting is a technique used to enhance the reasoning capability of large language model. It involves guiding the model to generate. This method has been given second generation because it has been shown to elicit impressive reasoning capability. Key concept chain of thought, sequential reasoning, structured input, demonstration, valid and invalid example, application across domain. Yeah, so answer looks really good for me. Now let's look at the paper that it has got. The paper that it has pulled in, and paper number 1 is Beyond Chain of Thought, a survey of chain of X paradigms for large language models. Contrastive chain of thought prompting. Shut up and let me think on why you should work on the foundation of quantum mechanics. I don't think this is relevant. Anyway, it's paper number 3. So with respect to the trying to evaluate this, just based on this one question, okay? Think if this is a rack system, again, understand I'm just trying to make this judgment based on one question. Ideally, the way we will do it is we will have a test data set or test set of questions, which we will try to do the same thing that I'm doing right now. So first, let's look at answer relevance. Okay, so can you explain chain of thought? Okay, the answer to me looks quite relevant, and I'm quite satisfied with it. So a complete take on that. Second, context relevance. The context that is pulled is Beyond Chain of Thought, survey of chain of X paradigms for large language models. So I do reckon it pulled a good paper to understand chain of thought or explain chain of thought to me. And probably the third is faithfulness. Okay, this is something that we need to understand. Chain of thought has been a widely adopted prompting method eliciting. Let's look at this paper. Okay, so ideally what I'm trying to understand is okay, so it's a chain of thought is a methodology that substantially enhances the reasoning capability element introduced by was prompting element with a structured format, input, thoughts, output. Okay. Alrighty. Now we'll spend some time understanding some intuitions behind building a good RAG architecture. Most of the things are quite intuitive, but it's always good to revise them before we delve deeper into building great RAG systems. As I've discussed before, a RAG system in itself is a system of systems where there are multiple subsystems which needs to be optimized properly to get a great RAG system. Now we'll look at these subsystems, get some intuitions around what needs to be really ticked off before you kind of start building and integrating them together. And hopefully that helps all of us build great RAG systems. So going forward with it, any RAG systems in essence will have an LLM as the generator. Okay. Then it will have a retriever. Now, retriever can be designed in multiple ways. As I discussed before, retrieval systems have a great history. It's not something new thing, but there are multiple ways it can be done. But the two major ways retrievers are designed are full text search or full text retriever. The second is semantic retriever. Okay, and then there is another type that is called as hybrid. Okay, which is a blend of these two. Now we have an LLM, we have a retriever. What else do we need? Third thing that basically I try to think about it is what I call as pre-production stage. Okay, pre-production stage. Pre-prod. Pre-prod stage is a stage where we get our retriever in shape so that it's able to get us the information, get us the context that a large language model might need at runtime to give a right answer. So at pre-production stage, things that need to be done are information extraction. What it essentially means is, like, for example, you're building a chatbot uh, for documentation of a coding repo. Then how do you take that information and pass it into a form which could be leveraged by a technology system? Okay. Second thing that needs to be done is something that's called as chunking. We'll discuss it in one of the future videos, but chunking essentially means is, suppose you have a 500 pages PDF, which is your whole information or the knowledge base of your organization. How do you split it into good intelligent chunks, which could be added to the context of a large language model without overwhelming the context and without overburdening on the cost, essentially per token cost. And final thing that's probably extremely important, that we have also covered in our project of the first video, is indexing. That using probably one of the different retrieval methodologies, how do you index your knowledge base in a form so that it's very easy to retrieve the corresponding right knowledge when a question arises from the user. So that's in essence is how you should probably think of a RAG architecture, that you have to decide upon a large language model. Okay, which large language model you have to choose. You have to choose on a retriever, and which retriever essentially works for your use case. And then you have to kind of make some decisions around the pre-production. Now, I didn't speak of a large language model in here because the assumption is most good large language model that you will probably use, whether it might be a Claude, it might be a GPT-4, or should do a decent enough job for you. But few of the consideration that you should always have when choosing a large language model are cost. There might be some use cases where when you delve deeper into it, a large language model might be just there to give a good user experience, and most of the good work essentially is happening from the retriever. So you might want to find a large language model which might be really optimized on the cost and can really convert the knowledge that it receives from retriever into a more digestible form for the user. And second, essentially, this you should probably also always think of is latency. Alrighty. Now, depending upon what your use case is, whether you want to host a large language model yourself or use one of the cloud providers, you might want to think of latency. Like if it's a chatbot that you're deploying, you might want a large language model that has really low latency. So you might want a small large language model deployed on your own cloud servers and so on and so forth. But yeah, that's about it. I think these are some things that I wanted to cover. That you have a large language model, you might have a retriever, and you think of something called as pre-production, and then based on different parameters, you might want to make all of the decisions. Most of these things will become much more clear as we keep on designing multiple systems, as we evolve this series of videos. But just keep this in mind. A RAG system essentially has a large language model selection that you need to do, has a retriever selection that you need to do, and how do you, and a pre-production phase where you need to decide how do you pass the information of a knowledge base, chunk the information, and index it. Okay, so that's about it. Alrighty, so before we delve a bit deeper into retriever systems and the types of retriever systems that help a RAG system become much more productive and efficient by identifying and adding the correct context to the large language model when answering a query, we should just once more spend some more time on retriever system, okay, and how it might look like. So this time we will go a bit deeper, okay. So in essence, without even thinking of large language model, a retriever system is based on a query or an information that is being probably punched in somewhere. Now this information system, this information hits the, what I should say, backend of the retriever system, which in essence has three main blocks, okay, which I've mentioned here. There is a first stage, there's a re-ranker, and there is modifier. Now all of these three together help us get the correct information or the correct context that's needed for that corresponding query which a user is trying to answer. All right. Now, this whole retriever backend is connected to a knowledge base And this knowledge base, there is another step which we'll cover as we move forward in the lecture, in which the knowledge base is converted into a form which is more suitable for a information retrieval system. And some of three main steps that you have to think of, that we also discussed in the just few minutes back in the same video, was information passing. Information passing is essentially data that is relevant for a retrieval system might be available in multiple ways. It might be in tables of SQL data sets. It might be in HTML files, it might be in XML files, but how do you pass it into a form which could be stored and readily accessible for the retrieval system to use it? Second is chunking. Now, if you think of it, if going back to a past example, archive papers, there are multiple ways you can literally think of information across papers, right? You could literally bunch together 3 or 4 papers from one particular stream into one, and that could be your one chunk. Or you could take one paper and split it into multiple different paragraphs, and each of them could be a chunk. Ideally, there is no right or wrong way of doing it. It all depends upon your use case or the problem that you're trying to solve. But in essence, it's said it's better off to store concrete chunks of information which can in themselves provide a sufficient amount of information to answer any particular query. Now, there are multiple ways of doing chunking. We will also go to that. And finally is indexing. Now, all of the information that you will have, whether it might be text or whether it might be some other multimodal images or videos or so on and so forth, they are all stored, but they need to be indexed and stored. What indexed and stored essentially means is indexes is a way of storing a data that allows us to later on go and retrieve it in a very, very efficient way. Okay, indexing is not particularly only from computer science space. It's basically started off in multiple other different streams, where it might be libraries where there are multiple books and you want to have a particular index so that you can go and basically get the right book, and other multiple places. So anywhere where you have to retrieve from a huge bunch of information or huge bunch of IDs, also I should say, this should be a way you should index them, so like you can easily go and search for a corresponding whatever you might need. Now, that is in essence in indexing. There is multiple ways in indexing is done in the industry. We have all moved to a stage where most of it is being captured by the semantic retrieval or using large language models, but still I do think there is also benefit in understanding some of the basics around indexing, because sometimes even the simple indexing methods work great for you. So in a sense, going back to this big box of the retrieval backend, there are 3 main small blocks in there. First is first stage. First stage in essence is where when a query comes in, the retrieval system tries to take the query and tries to find the top candidate chunks from the knowledge base, which might be closer to the query or answering that particular query, right? It doesn't try and get the perfect answer, but tries to get like top 5 or top 10, depends upon how much you are concerned about latency and other factors. But that's what basically the first stage is. Second is re-ranker. Re-ranker is where we actually go on and take, you have your own way of taking this 4 or 5 different candidate context and converting it, or selecting one particular context that could be added to a large language model. And finally, modifier is where you actually take the final context and modify it in a way which might be suitable for the downstream large language model to act on and generate a particular output. So in essence, this is a retrieval system. I've gone a layer deep so that you actually understand how a retrieval system basically works. Again, just quick revision. Query comes in. There is the first stage which takes that query and tries to find from knowledge base top candidates which might answer that query. Re-ranker that takes those candidates and gets or either compresses them into one, or tries and find one particular context that might be suitable for the query that we are trying to answer. And finally is modifier, which modifies the context in a way which might be suitable for the large language model. So in essence, this is a retrieval system. Now let's go into details. Alrighty, now let's look at some types of retrieval systems that you will find in the wild. They are majorly, you will find either of these 4 retrieval systems when you are trying to build a retrieval system or working on retrieval systems. And each of them have their own pros and cons, and which we'll also discuss further in the video. But just Right now, what I want everyone to do is just try to build an intuition around all of these, right? So essentially, there are four types of retrieval systems. First, exact or Boolean search retrieval. Second, full text retrieval. Third, semantic retrieval. And fourth, hybrid retrieval. Alrighty. Now, we'll talk about each of them now in detail. We'll start off with exact or Boolean search retrieval. Okay. So the exact or Boolean search retrieval, in essence, is where you write a particular query and some of the different corresponding subjects out of it are directly used in a Boolean equation to search from a particular text or search from a particular database. It's as simple as that. Think of it like literally of, if those of you who are familiar with SQL, how you in a SQL you query a particular database to get a particular row. That's probably a example of a Boolean search. Now there are further processing steps that are involved within it, where a query is taken, it's probably stemmed and lemmatization is done, and you probably identify the subject and then you put it into a Boolean search. But in essence, that's what it is. It doesn't search for the whole context essentially, or like for example, if someone is asking what are some top restaurants in Australia, the whole exact search engine particularly is only probably meant for where it looks at it, it converts and gets it and sees Australia and basically plugs it into where you need it in a country format. So that in itself is exact or Boolean search. Second, we'll look at the full text search. Full text retrieval is what we have been doing so far in some of the examples and projects that we have been building in the video, where the knowledge base in itself is converted into term frequency, inverse document frequency, sparse vectors. Sparse vectors are because, like for example, if you're looking at a particular text chunk, out of all the different term frequencies or different words, most of them will be zeros, right? There are only few places where you will see one. Therefore, it's called a sparse vector. And you mainly take the query that you get and you use cosine similarity to identify that which of the chunks stored in the knowledge base are closer to the query that is being asked. That in itself is a full text retrieval. Third is semantic retrieval. Semantic retrieval is something that's probably the most popular right now, where the knowledge base, different chunks of the knowledge base are converted into vector embeddings using deep learning models. The reason why it's become more popular, and probably you will see it topping the charts of the metrics across the different retrieval systems, is the deep learning models convert the knowledge chunks into a better representation of the overall language and overall understanding of it. Like for example, it could help you understand whether a king and a queen both are probably somewhat, there is a similarity between both of them. I will link some papers down below people who are probably interested in understanding embeddings and all of this stuff. But this is how it is. This is more of a dense vector, and you mainly to search through it and to identify the candidates and do re-ranking, basically different other methodologies like in approximately neighbor, fast, and different other terms and things are used that we'll further see as we move in the lecture. And finally is hybrid retrieval. Hybrid retrieval can take multiple forms. Hybrid retrieval in essence is where you try to take the best of, let's say, semantic search as well as text search as well as probably exact search, and depending upon the use case you might use all of them. And like for example, in first stage where you are trying to get candidates before the re-ranking, you might just use a full text search and get the candidates. Post that, you might use a semantic search to re-rank them and basically then send it across to a large language model. Second way it can be done is you can come up with a score, and that score could be based on full text search as well as semantic search. You add them and basically then send it across. So multiple ways it could be done, depends upon your experimentation and how do you model it. So this in itself is how 4 different retrieval systems essentially exist, and everything that you will probably see basically will fall in these 4. The most popular right now are probably semantic search and hybrid retrievals, and which are probably topping the charts across RAG systems, which we'll be looking at in much more detail as we move forward. Alrighty, so before we proceed and do some examples and quick implementation of some retrieval systems, let's quickly again compare all the 4 types of retrieval systems whom we just saw. So starting with the exact match, its key feature is strict equality based retrieval. Second is full text search, which searches through your corpus using keyword and relevance ranking like TF-IDF, term frequency, and there are multiple ways of doing it. Semantic retrieval, it's meaning based and embedding similarity, right? So it allows us to find different sentences, although they might not be textually similar, but semantically or meaning wise they might be similar. And finally is hybrid retrieval, which tries to combine all the different retrieval types that we just spoke about and tries to get the best out of it. The strengths are exact match is absolutely fast and precise. Most of them that I've seen actually use SQL engine underneath it, and probably SQL is one of the most tried, tested, one of the most robust system in the world. Extremely fast and precise. You can optimize it as per different data types and so on and so forth. So extremely fast and precise. Limitation in that is there is no flexibility in query variation. It literally is there is a templated queries that exist depending on the questions that are coming through. You just plug in the particular Boolean algebra in there and just change few stuff and just basically run it. So it's a bit I will say unsophisticated, but it's extremely fast and precise. Full text search is good for unstructured data, but it doesn't have limited semantic understanding. Like for example, things like if you're asking for who are the closest monarch to the King of England, you probably might not get anything in the corpus if the words like monarch or king doesn't exist in a corpus. It might have something else. It might have leaders closer to the King of England or something like that. Third, semantic retrieval. It captures semantic relationship really well, and that's the reason why you will see most of the semantic new retrieval system implementation, almost all of them, whether it might be a search or it might be a document lookup, they all try to use semantic relationships. But the limitation is it's quite computationally intensive. You need a deep learning model to continuously keep on changing your embeddings and basically keep on updating them. And finally is hybrid retrieval, where based on your use case, you might use just a little bit of semantic retrieval and the rest of them might be an exact match or full text search or the other way around. But the limitation with the hybrid retrieval is the complexity in implementation. There is more work that is needed in terms of the engineering and designing different smaller systems, different data flows, and that takes a bit of work. So yeah, these are the 4 retrieval system. Keep in mind, think about all of these whenever you have a retrieval task in your hand and try to implement them. Now let's look at some examples finally. All right, so now let's look at some examples on implementations of retrieval systems. So this is something that I have already built. We'll go through the code in a bit, but in a sense, it's a kind of a, like I should say, mock mini search engine based on the same archive data set that I mentioned before, and we have probably leveraged in the first video and probably even in the initial part of this video. But this is mainly a search engine which allows you to search through that corpus using all the 3 major functionalities or 3 major types of search: semantic search, BM25, this is a type of lexical/textual search, and exact match. Okay, and what we'll do is we'll do this and it will, over a period of time, as we do this, it will become apparent of what each of them does and what are the benefits of each of them. Okay, so the query that I'm trying to find is among all the archive papers is logistic regression based finance models. Okay, so let's see what kind of search it gives us. Click it. Oh, sorry, we are doing exact match. So in the exact match, when we are doing logistic regression based finance model, we didn't get anything. Like literally anything. So essentially, because what exact match does is it goes in and like literally searches through the abstract of all the papers that are in this data set. Is there something called a logistic regression based finance models? If it doesn't exist, no search results. Okay. Now let's look at BM25. Okay. What do we get? Okay. So we've got some stuff like, for example, we've got integration, non-stationary time series, stationary, non-stationary increments. In this, we have like a regression written somewhere. So maybe that's the reason why we are getting this. But still, class integration was classified this. And it's okay. It's something, but still a flexible Bayesian generalized linear model for dichotomous response. Application text categorization. Again, nothing related to finance in here, but because it has regression and should mention here, we got this. So similar kind of results, not that relevant, but you get what it's, because it's a lexical match or a textual match. It went in and tried to find the corresponding like words like regression, logistic, or finance model, but it didn't get anything. Now let's finally look at the semantic search. Okay, let's click on semantic search. Okay, good. Now we are getting parametric and non-parametric models and method in financial econometrics. Quite relevant. Okay, we'll search for logistic regression based finance model, because what semantic search does is it doesn't try to match words in the search corpus, but tries to find corresponding semantic meanings. So because I'm using logistic regression based finance models, it's looking for parametric as well as non-parametric models in there, and then it gives us a quite a decent enough first paper. Second is again trading strategy based on the second law of thermodynamics, which I still feel is quite relevant. Pre model for stock market fluctuation. So most of them generalize half logistic distribution authors. So quite relevant. I would say at least from one example that we just saw, the semantic search is giving us quite relevant answers, and that is the reason semantic search is literally ruling the world of retrievers, or ruling the world of retriever search. We hardly find anywhere where people are not doing semantic search. The only reason that you will find it is if your corpus is really small, really narrow, plus you don't want to have so much investment on your like processing power and so on and so forth. We already had a look at the table which told us what are the advantages and disadvantages of that. So this in itself explains you all the three major types of retrievers and how do they help you and what they can do for you. Now in exact match we didn't get any output. Let's try and let me show you something. I will take this on type 3 or something from a particular paper and see dynamics inspired. Maybe we do the predator prey population evolution. Okay, and let's see what do we get here. And we do an exact match. So predator prey model for stock market fluctuation, present a dynamic model for this. So as you see, like it goes in and searches for the exact match in there somewhere. So in here, if you go through it, oh yeah, so it literally went in and searched for one and found it in this particular paper. Predator population evolution is in this abstract, so it gave us that output. So that's what exact match does. Now let's quickly have a look at the code. I will anyways have this code mentioned in the description of this video, so you can have a look at it. Pretty simple code. What it literally does is it uses BM25 semantic for semantic search. It uses sentence transformer, and for exact search, it's literally a simple we search for a string if there is a particular word that exists. Then it's a normal Gradio based interface which tries to use all of them and runs the search on the abstract, not on the title or anything else. So that's about it. I think in this video we did really well. We further went deeper into the retriever aspect of Retrieval-Augmented Generation. We understood how important that is. Now, if you see right now, this in itself is a discipline. It's a wider discipline. And on top of that, what a generation or LLM-based generation does, it makes the user interface much more clear. So just keep that in mind. We will further delve deeper into how the retriever and generator work together and how do you further try to optimize the whole system as a lot. But always what I suggest is always start with the retriever first. If you are working with the absolutely greenfield problem, start with retriever first. Build a gold standard data set. Ideally, the way the evaluation will happen, like what I did here is we just picked one or two queries and saw like from human, that is my judgment, if it's working or not. But ideally what we will have is you will always have a gold, what I call the gold test set, in which you will have, okay, for this kind of query, this is the corresponding ranking that I should expect from the corpus. And then accordingly, you will probably see what are you getting out of a particular retriever model, and then do something like a Pearson correlation or some other metric to check if it actually matches with what a human might actually expect. So that's about it. Build a good test set, try to evaluate your retriever well, and yeah, we'll further see how we can join it to a generator and look at some other stuff as we move forward. So yeah, that's it. See you next time. Bye.